Welcome back to the deep dive. Today, we are undertaking a journey to a place that is perhaps the most difficult physical location to study in the entire universe.
And that's not because it's millions of light years away.
No, exactly. It's because it is literally right beneath our feet. We are diving deep into the Earth's interior.
It really is the ultimate blind spot in planetary science. I mean, we can't physically go there.
Not even close.
We can't even send a probe down effectively. So we have to rely entirely on, deduction, inference, and this meticulous interpretation of things like vibrations and gravity fields to understand the vast majority of our own home planet.
It is, as you said, global scale detective work.
That's the perfect phrase for it.
Absolutely. Our mission today is to synthesize these incredible feats of geological research, the complex physics of seismic waves, and the dynamic output of volcanoes to really reveal the hidden structure and that ferocious heat engine shaping our planet.
Right.
We want to give you a shortcut to understanding the structure and power of the Earth from the crust all the way down to the core.
And I think we have to start by just appreciating the sheer scale of the challenge here. The Earth is immense.
It's hard to wrap your head around.
It really is. Its radius, so that's the distance from the surface right down to the dead center, is approximately 6,378 kilometers.
6,378.
That distance is the whole reason why every technique we use is indirect. The pressure and the temperature, they rapidly become astronomical.
You would crush anything.
Crush and melt any equipment we could conceivably deploy. It's just off the table.
That's the initial hook right there, isn't it? The sheer impossibility of it. So why dedicate so much scientific effort to studying something we can't even touch?
Well, because understanding these internal processes, what geologists call endogenic processes, is absolutely vital.
Right.
They are responsible for every major feature we see on the surface. We're talking mountain building, continental drift, and they drive these catastrophic events like massive earthquakes and tsunamis.
So if you want to understand why continents look the way they do, or why mineral deposits form where they are, or even why the ground might shake tomorrow,
You have to understand the heat engine that's running thousands of kilometers below us. Without that internal energy, our planet would just be a dead, flat, geologically inert rock.
a bit like Mars or the Moon.
Exactly like Mars or the Moon. No plate tectonics, no volcanism, nothing.
Okay, let's unpack this. We've established the incredible depth, the extreme heat, the pressure. If we can't, take a road trip to the center, how do we even begin to figure out what materials are down there and what state they're in?
We have to start with most basic evidence, the limited view that's provided by what we call direct methods.
Okay, so what we can physically touch and analyze.
Right. And the direct methods are straightforward, but honestly, they're genuinely humbling in their limitations.
Why so?
They primarily involve mining and analyzing rocks found on the surface and from underground mines. For example, you take the deepest mines we operate, those incredible gold and platinum mines in South Africa. They manage to reach impressive depths of about 3 to 4 kilometers.
3 to 4 kilometers. That sounds incredibly deep for a mine.
It is for a mine,
Yeah.
but it only gives us these precious samples of the uppermost crustal rock. It allows us to analyze less than 0.05% of the total radius to the center.
0.05%. So it's just scratching the paintwork.
Not even. And scientists have, of course, tried to push that boundary with dedicated deep drilling projects. These things become engineering marvels in their own right.
And the most famous of these is the Kola super deep borehole, right? Up in Russia.
That's the one, located in the Arctic Ocean region. It was an incredible achievement, running from 1970 all the way into the early 1990s. But after decades of effort dealing with equipment failure from heat and pressure, it only reached a depth of 12 kilometers.
12 kilometers, so 3 times deeper than the mines, but still.
Still, it illustrates the visceral problem perfectly. At just 12 kilometers down, the temperature was already approaching 180 degrees Celsius.
Wow.
Which was far, far higher than they had predicted.
So even with heroic engineering, 12 kilometers barely registers as a pinprick when the goal is over 6,000 kilometers.
It's a rounding error.
It just shows us that relying on direct sampling to gather global information is, well, it's fundamentally impossible. The geothermal gradient, that increase in heat, is simply too steep.
Precisely. So if drilling and mining only give us that thin top layer, what's the next best direct method?
I imagine it's something that brings the deep stuff to us.
You're exactly right. We rely on nature's own transport system, volcanic eruptions, These are our natural deep Earth sample carriers.
That's a fascinating way to think about it. So volcanic activity acts like a geological syringe, bringing molten material up from the depths to the surface where we can get at it.
Exactly. When that molten rock, which we call magma when it's underground, is brought to the surface as lava, we can analyze its composition.
And because that magma forms in the deeper layers.
Right, it forms through partial melting in what we call the asthenosphere or other upper mantle regions. So laboratory analysis of that erupted material gives us detailed chemical clues about those deeper, inaccessible layers.
For instance.
For instance, the high density of basaltic lavas points directly to the kind of dense iron-rich minerals that we now know dominate the mantle.
Okay, so the direct methods are limited, but they do confirm our models for the crust and the very top of the mantle. But the real heavy lifting, the bulk of what we know, that has to come from the indirect methods.
This is where we transition from brute force sampling to clever deduction. It's the detective work.
Where do we start with that?
We begin this detective work by analyzing fundamental physical properties. We know empirically that temperature, pressure, and density all increase significantly as you go deeper.
Right.
By knowing the total mass of the Earth, which we can calculate from its gravitational pull and its volume, scientists can use these complex equations of state to calculate exactly what the expected pressure and temperature values must be at the very center.
So you have a baseline. You know what the final numbers have to add up to.
It gives us crucial boundary conditions for our models, even before we bring in any other data.
And what's truly mind-bending here is that we rely on objects from space to help us figure out our own planet's interior. We look at meteors.
It sounds strange, doesn't it?
It does. How does space junk inform us about our planet's guts?
Well, meteors, particularly the iron-nickel ones and certain stony types called chondrites, are incredibly valuable as proxy data.
Proxy data.
Yeah. They're residual solid bodies from the early formation of the solar system, just like Earth. It's theorized that when our planet formed, the heavy elements, the iron and nickel, sank to form the core through a process called differentiation.
So these meteors are like the leftover building blocks.
Precisely. Analyzing these metallic meteors provides us with the best-case scenario for the composition of our own planet's deep interior, especially the core. They're essentially the materials that didn't get swept up into a big planetary body.
That's a brilliant connection. Okay, so we're also measuring forces we can detect from the surface, like gravity. And we know gravity isn't totally uniform across the globe, right?
It's not. It's a little stronger at the poles and weaker at the equator, mostly due to the Earth's rotation and its slight bulge. But more importantly, there are local variations.
And this leads to the concept of gravity anomalies.
These are absolutely critical for mapping the subsurface. A gravity anomaly is defined as the difference between the gravity we expect to measure in a given location, based on a smooth, uniform Earth model, and the gravity we actually measure.
So if I'm standing somewhere and I measure a slightly higher gravity than expected, what does that tell me?
It indicates a positive gravity anomaly. It means there is extra mass, some unusually dense material concentrated right beneath the surface where you are.
And the opposite.
A weaker than expected reading, a negative anomaly, indicates less dense material, maybe a large subsurface cave system or a thick region of lighter sedimentary rock.
And geologists use this for, what, finding minerals?
Extensively, especially for locating high-density ore bodies like iron. It gives us these highly localized clues about how varied the crust is just beneath our feet.
And the last of these indirect methods is magnetic surveys.
Right. Magnetic surveys are primarily useful for mapping the crust and the upper mantle in great detail. They help us specifically locate and map the distribution of magnetic materials, primarily iron-rich minerals.
So it's not telling us about the deep core.
No, the deep core's magnetic properties are a whole different system related to the planetary magnetic field. This is more about mapping shallow structures, things like dikes, sills, and certain ore deposits. It just adds another layer to our understanding of the upper layers.
So all of these methods combine, they give us precious fragments of the puzzle. But if we had to pick one single category of data that completely revolutionized our understanding, the true hero of this deep dive, it has to be listening to the Earth.
Seismic activity.
Seismic activity, earthquakes.
Without a doubt. Without seismic waves, we would still be wildly speculating about the existence of the core, the mantle, the boundaries between them. The data we get from earthquakes provides definitive, empirical proof of those hidden layers and their states of matter.
Let's start with the basics then. What exactly is an earthquake, beyond just, the ground shaking?
An earthquake is the instantaneous shaking of the earth caused by the sudden, violent release of accumulated energy. And this release happens along a fault.
It was just a crack in the crust.
Essentially, yes, a fracture or a zone of weakness. The mechanism relies on elasticity. The rocks on either side of the fault are constantly being pushed and pulled by immense tectonic stresses. They're trying to move, but they are locked in place by friction.
It's like stretching a giant rubber band until it finally snaps.
That is the perfect analogy. They store this elastic potential energy. And when the accumulated stress finally overcomes that frictional lock, the rocks abruptly slip.
And that snap releases all that stored energy.
It's released in the form of seismic waves that propagate outward, just like ripples in a pond.
And for anyone looking at seismic diagrams, we need to clarify two key location markers. The point deep underground where the energy is actually released, that's the focus.
Or the hypocenter, yes. And critically, the point on the surface directly above that focus is the epicenter.
Right. And the epicenter is what you always hear about on the news.
It is, because that's where the most intense immediate shaking is often felt. But the depth of the focus plays a huge role in the extent and type of damage. Shallow focus earthquakes are usually far more devastating near the epicenter.
Okay, now we get to the physics that unlocked the Earth's secrets. The body waves. These are the vibrations that travel through the bulk of the planet.
And there are two main types of body waves. Their properties are mutually exclusive, which is why they are such powerful diagnostic tools.
Let's start with the first to arrive.
First, you have the P waves, or primary waves. They are compressional waves. This means they move by squeezing and stretching the material they pass through.
We mentioned this earlier. It's a bit like sound waves.
Precisely. They vibrate parallel to the direction the wave is traveling. Imagine pushing and pulling a slinky. They create these temporary differences in density within the rock.
And their crucial characteristic.
They are the fastest of all the waves, so they arrive first at any seismograph station. And this is key. They have the ability to travel through gases, liquids, and solids.
So they're unstoppable. They can go through anything.
They can, though their speed changes depending on the material. But then you have the secondary waves, the S waves.
And these are the game changers.
These are the absolute game changers. S waves, or secondary waves, arrive later. They are shear waves.
Shear waves. What does that mean?
It means they vibrate perpendicular, so vertically, up and down to the direction of travel. They create crests and troughs. Imagine shaking a carpet or a rope. They don't compress the material, they twist and shear it.
Okay, so a totally different motion.
A totally different motion, but here is the monumental insight. S waves can travel only through solid materials.
Only through solids. And that single physical limitation is what allowed scientists, using seismometers scattered across the globe, to peer into the center of the Earth.
It's the ultimate empirical proof. Liquids do not support shear stress. You can't twist water, it just flows.
Right, it has no rigidity.
Exactly. Therefore, if a liquid layer exists deep inside the Earth, the S waves must be completely blocked by it. The very lack of a signal told us more than any direct sample ever could.
That's incredible. So just to complete the picture of the seismic energy, once those body waves, the PNS waves, reach the surface.
They interact with the surface rocks and they generate surface waves. These are often lumped together as L waves.
And these are the ones that do the damage?
They are generally the last to be recorded on instruments because they travel along the surface boundary, but they are by far the most destructive.
Why is that?
Because they have the largest amplitude, and they involve both a horizontal and a vertical rolling motion across the surface. They are the waves that are responsible for ripping up roads, causing landslides, and collapsing buildings. They cause the most visible, widespread damage.
Okay, so let's visualize the seismic data because the maps showing where the waves don't appear are the most telling evidence. We are talking about shadow zones.
A shadow zone is exactly what it sounds like. It's an area on the Earth's surface where seismographs, for physical reasons, do not detect the waves generated by a distant earthquake.
It's not a lack of instruments, it's a genuine lack of a signal.
That's right. If the Earth were a uniform, solid ball, we would register both P and S waves everywhere after any given earthquake. But we don't.
We see that P waves are recorded everywhere except for this wide band between 105 degrees and 145 degrees away from the epicenter.
And that gap is critical. It's caused by refraction or bending as the P waves transition from the solid mantle into the liquid outer core.
They change direction.
They do. P waves hit that boundary. And because the outer core is significantly denser, but also less rigid than the solid mantle above it, the waves slow down dramatically and they bend inward. This change in direction prevents them from hitting the surface in that 105 to 145 degree zone.
So it's a focusing effect almost that leaves a shadow.
A great way to think of it. But the S-wave shadow zone, that tells the definitive story about the state of matter down there.
And it's much bigger, right?
It's dramatically larger. It extends beyond 105 degrees from the epicenter and covers over 40% of the Earth's entire surface.
40%.
And unlike the P waves, which just refract, the S waves are completely blocked. They cease to exist because they simply cannot shear the liquid outer core.
So the fact that any monitoring station more than 105 degrees away from a quake's epicenter will never register an S wave.
That is the hard, undeniable evidence that confirms a massive, churning liquid layer inside our planet.
It's difficult to overstate how pivotal that realization was in the early 20th century.
Okay, moving on from the wave mechanics, let's look briefly at how we classify and measure the seismic events themselves. Our sources list 5 distinct types of earthquakes based on their mechanism.
Right. The vast majority, the ones we always think of, the ones responsible for plate tectonics, are tectonic earthquakes. They're caused by stress and movement along faults.
The classic kind.
The classic kind. Then you have volcanic earthquakes. These are usually much smaller events caused by the movement of magma and gases beneath active volcanoes. They often serve as a warning sign of an impending eruption.
And we also have some human-induced types that really speak to our impact on the planet, like collapse earthquakes.
The collapse quakes are very localized events. They're typically caused by the sinking or caving in of the roofs of underground mines or large caverns, generally shallow and weak, but they can be destructive locally.
And then, unfortunately, explosion earthquakes. Caused by large nuclear tests or major chemical detonations, they create seismic waves that can be tracked globally, which is actually how nuclear test ban treaties are monitored.
And finally, a really fascinating modern phenomenon: reservoir-induced earthquakes. That just sounds counterintuitive. How does water cause an earthquake?
It's a compelling mechanism, and it all comes down to pressure. When you build a massive dam, the sheer weight of the millions of tons of water in the reservoir, combined with water seeping deep into the ground, increases what's called the pore pressure within the rock structure beneath the dam.
So you're forcing water into all the tiny cracks.
Exactly. And this increased water pressure can act as a lubricant. It reduces the friction holding existing faults in place, causing them to slip prematurely and trigger tremors.
So we are directly causing geological instability.
In some cases, yes. It's a direct link between large-scale human engineering and seismic activity.
And regarding frequency, we always worry about the massive catastrophic earthquakes, a magnitude 8 or higher, but those are statistically pretty rare.
They are, thankfully. A massive, great earthquake occurs maybe once every 1 to 2 years somewhere on the globe, whereas tiny, imperceptible tremors that only sensitive instruments can pick up.
They're happening all the time.
They happen almost every minute somewhere around the world.
Yeah.
The Earth is truly never static.
So finally, let's talk about quantifying them. We use 2 main measures that often get confused in media reports. There's the magnitude,
Measured by the Richter scale. This quantifies the actual energy released at the focus. It's a logarithmic scale rated from 0 to 10.
and the logarithmic part is really important to understand.
It's crucial. Because it's logarithmic, a magnitude 6 earthquake is 30 times more powerful, releases 30 times more energy than a magnitude 5. It's not a linear increase.
Right. And the other scale is intensity.
That's the modified Mercalli scale. This one is subjective. It measures the effects, the visible damage, and the perceived shaking on the surface. It's rated with Roman numerals from IN not felt to 12. Catastrophic destruction.
So if the Richter number tells me the raw power of the event itself, the Mercalli scale tells me how badly my coffee table shook, or, whether the building collapsed.
That's a perfect summary.
So just for context, what would be the difference between, say, a Mercalli S-nth and a Mercalli X?
A Mercalli S7 is very strong. At that level, most people are alarmed. You'll see some damage to poorly constructed buildings, but well-built structures are generally okay.
Manageable.
A Mercalli X, however, is classified as extreme. Now you're talking about many buildings being destroyed, train rails getting bent, significant landslides.
Yeah.
It's the difference between significant disruption and total catastrophe. We need both metrics to properly assess risk.
Excellent. Okay, now that we have established how we collected the data largely through those seismic wave velocities and their shadow zones, we can transition smoothly into the scientific conclusion. Earth's layer cake.
The structure. Right. The Earth's internal structure is defined by those abrupt changes in seismic wave velocity, which occur at very specific depths. Those velocity jumps signal a change in density, composition, or the state of matter.
And starting at the surface, we have the crust.
The crust. It's the outermost solid, brittle part of the planet.
And we learned there are two fundamental types of crust, right? They differ hugely in thickness and composition.
They do. You have the oceanic crust, which is relatively thin and dense. It's primarily made of basaltic rock and averages only about 5 kilometers thick. It's what underlies all the ocean basins.
And then there's the stuff we live on.
The continental crust. It's much less dense, more granitic or felsic in composition, and it's far, far thicker. It averages about 30 kilometers deep.
And under major mountain ranges, like the Himalayas, that continental crust roots deep into the planet.
Oh, absolutely. Under areas of continental collision, it can become immensely thick, extending up to 70 kilometers down.
70 kilometers. So continental crust can be more than 10 times thicker than oceanic crust.
In some places, yes. And the boundary between the base of all that crust and the top of the mantle is marked by a very clear, sharp increase in seismic wave velocity. It's known as the Mohorovičić discontinuity.
Or just the moho, for short.
The moho. Much easier to say.
Beneath the crust is the vast layer we call the mantle. It extends almost halfway to the center of the Earth.
The mantle is enormous.
Okay.
It extends all the way down to a depth of 2,900 kilometers. It's predominantly solid silicate rock, but it is not uniform. We have to subdivide it into layers based on its mechanical strength.
And the most rigid outer layer, the one that makes up our tectonic plates, is the lithosphere.
Right. The lithosphere is the crust combined with the uppermost solid, brittle part of the mantle.
So it's a structural layer, not a compositional one.
Precisely. The lithosphere is strong, and it ranges widely in thickness, from maybe 10 kilometers beneath oceanic ridges to 200 kilometers thick under the old, stable continental interiors.
And directly beneath that rigid plate is perhaps the most critical zone for understanding plate tectonics, the asthenosphere.
Ah, the asthenosphere. This is the region where the rock is so hot that it becomes slightly plastic.
So not liquid, but pliable.
Yes. The asthenosphere is the upper, weaker portion of the mantle. It occupies roughly the top 400 kilometers below the lithosphere. It's not liquid, but the temperature and pressure are balanced perfectly to allow it to behave plastically over geological timescales.
What's a good analogy for that?
Think of it not as liquid water, but more like very thick, slowly yielding tar or highly viscous putty.
And that plasticity is absolutely crucial. It's what allows the rigid tectonic plates above it, the lithosphere, to move, glide, and slide across the surface of the planet.
It is the great lubricating layer. Furthermore, the asthenosphere is identified as the primary source of magma. This is the layer where decompression melting occurs due to upward convection, generating the molten material that feeds volcanoes and creates new crust.
So the convection currents that drive the whole system are in the asthenosphere.
The massive, slow convection currents that drive heat from the core outwards, providing the ultimate engine for plate tectonics, are facilitated by the hot, ductile nature of the asthenosphere.
And that leads us, finally, to the innermost region, the core.
The core. It starts abruptly beyond the mantle at 2,900 kilometers down and goes right to the center. We deduce its composition from meteorite analysis and the absolute requirement for Earth's known density and rotational characteristics.
It has to be heavy stuff.
Extremely heavy materials, primarily nickel and iron. Geologists often just call it knife.
And here we bring back the seismic data. The core is not uniform. It has that major division we discovered with the S waves.
Correct. The core is clearly bifurcated. You have the liquid outer core, which is that massive layer that blocks the S waves and is responsible for generating the Earth's magnetic field through the movement of liquid iron.
And inside that
Is the solid inner core at the very center.
which raises the essential question. If the outer core is liquid because of the extreme heat, why is the inner core, which is even hotter, estimated up to 6,000 degrees Celsius, like the surface of the sun? Why is it solid?
It is entirely due to intense pressure.
Pressure just wins.
Pressure wins. While the inner core is indeed the hottest region of the planet, the pressure exerted by the surrounding 5,000 kilometers of rock and liquid iron is so overwhelming, we estimate it at 3.5 million times atmospheric pressure, that it forces the iron and nickel atoms into a stable, tightly packed, solid crystalline structure.
So the pressure literally squeezes it solid, even at those temperatures.
The mechanical energy of pressure overrides the thermal energy of heat, preventing the atoms from moving freely. That solid ball is rotating, and it's essential for the global dynamics we've been discussing.
That is truly mind-boggling. Okay, so now let's bring the discussion back to the surface, focusing on the dynamic results of all that internal heat and pressure, volcanoes and the landforms they create.
This is the surface manifestation of the asthenosphere at work.
the end of the conveyor belt.
Exactly. A volcano is simply the vent through which gases, ash, and molten rock escape to the surface. And the shape of the volcano tells us everything we need to know about the properties of the magma beneath it. We categorize the structures they build as extrusive forms.
Let's start with the giants, the largest volcanoes in terms of volume. Shield volcanoes.
Shield volcanoes, and the classic example is always Hawaii, are massive, but they're very gently sloping. They resemble a warrior's shield lying on the ground.
Hence the name.
Right. They're built almost entirely from basalt lava, which is very fluid. We call that low viscosity. Basalt is low in silica, which allows the lava to flow easily and rapidly for great distances before it solidifies.
So that fluidity is what prevents them from building up a steep cone. They just spread out instead.
Precisely. Their eruptions are generally non-explosive, they're effusive, they're characterized by these beautiful lava fountains and slow-moving rivers of molten rock.
Unless water gets involved.
Unless, as you mentioned, an external factor like water entering the system introduces steam, which can cause phreatic explosions. But generally, they are monuments to quiet, persistent volcanism.
So let's contrast that fluidity with the composite volcanoes. These are the iconic steep-sided mountains we often picture, like Mount Fuji or Mount Vesuvius.
Composite volcanoes or stratovolcanoes are a completely different animal. They erupt cooler, much stickier, or viscous lava.
And that's because it has more silica in it.
Exactly. This magma is usually andesitic or rhyolitic, meaning it's high in silica. That high viscosity means the lava doesn't flow easily at all. It piles up right around the vent, creating those classic steep slopes.
And that stickiness has a critical, dangerous side effect: high explosivity.
It traps immense amounts of volcanic gases. As the magma rises, the pressure decreases, and those dissolved gases try to bubble out. But if the sticky lava forms a plug in the conduit, the pressure just builds and builds until it overcomes the resistance.
And then
A cataclysmic, highly explosive eruption that ejects ash, gases, and rock fragments high into the atmosphere. They were built layer by alternating layer from these explosive ash falls and thick lava flows.
Then you have the most extreme case, which doesn't even build a mountain, it destroys one: the caldera.
A caldera is a massive feature. It occurs when a volcano's magma chamber is emptied extremely rapidly, usually through a super eruption. Once the structural support beneath the volcano is gone, the entire thing collapses inward on itself.
So it's a collapse feature.
The collapse following the eruption is what defines them. It forms a vast, often circular depression. We see famous examples like Yellowstone or Toba in Indonesia.
We also have to acknowledge the immense scale of flood basalt provinces. These aren't cone-shaped vents at all, are they? They're vast sheets of rock.
These are large-scale fissure eruptions. Highly fluid, low-viscosity basaltic lava is released over vast linear cracks in the crust, and it just flows for hundreds of kilometers, covers colossal areas, sometimes hundreds of thousands of square kilometers.
And the famous example is the Deccan Traps in India.
The Deccan Traps are the classic example.
So what is the significance of something like that, beyond just its sheer size?
Their temporal and climatic significance is enormous. The Deccan Traps cover an area roughly the size of France, formed by millions of cubic kilometers of lava over a period of less than 1 million years. The sheer volume of gases and dust released during these long-term, massive eruptions are strongly linked to major climatic shifts and potentially even mass extinction events in Earth's history.
So it highlights that profound connection between deep Earth processes and surface biology.
A very direct and dramatic connection.
And finally, perhaps the most globally significant volcanic feature, one that runs unseen across the globe: mid-ocean ridge volcanoes.
This is the largest volcanic system on the planet, and it's operating 247. It is a 70,000-kilometer-long chain of undersea mountains and fissures that runs through all the world's ocean basins.
70,000 kilometers.
It's the seam of the Earth. This is where new oceanic crust is continuously being created through seafloors spreading as magma rises from the asthenosphere. It's the engine that literally builds the tectonic plates.
So we've covered all the stuff that makes it to the surface, the volcanic or extrusive rock. But what about the molten rock that cools deep underground, the stuff that never reaches the surface?
We call these intrusive forms, or plutonic bodies.
Plutonic, after Pluto, the god of the underworld.
Exactly. Intrusive forms are the solid shapes magma takes when it solidifies inside the crust instead of erupting. These plutonic rocks are vital because they tell us about the plumbing system of ancient volcanoes.
But we only see them after the fact.
Right. They only become visible millions of years later after all the overlying rock and soil has been stripped away by erosion.
Okay, let's start with the big ones, the colossal masses of magma that cool deep down.
Those are the batholiths. These are truly huge, irregular bodies of cooled magma. Because they're so massive, their emplacement often drastically alters the surrounding country rock.
And when they're exposed.
When they are finally exposed by erosion, they can form enormous dome-shaped granite masses, sometimes covering thousands of square kilometers. They are the roots of ancient mountain chains.
Then you have smaller but more visually complex forms, like laccoliths.
A laccolith is a distinct dome-shaped intrusion. It pushes the overlying rock layers upward, but it maintains a flat base, and it's connected to a pipe from below. It literally buckles the overlying strata into a dome.
And our sources note these are notably found in places like Karnataka in India. Why there specifically?
Karnataka's geological history involves significant periods of stable erosion and uplift. The overlying softer sedimentary or metamorphic rock has been systematically removed over eons, exposing these dense, resistant dome-shaped plutonic bodies. They often form distinct hills or features in the landscape.
And if the laccolith is a dome pushing up, what's the opposite? The lapolith.
The lapolith is the inverse. It's magma that cools in a distinctive saucer shape, so it's concave to the sky. It usually forms in a depression or a basin where magma has pooled and solidified.
And then there's the phacolith, which is tied directly to the folding of the rock strata.
Yes, phacoliths are these lens-shaped, wavy masses of rock found specifically at the hinge areas of folded rock strata. So they're either nestled at the bottoms of synclines, the downward folds, or capping the tops of anticlines, the upward folds. They can form perfectly to the undulations of the folding.
Then you have the more straightforward horizontal and vertical intrusions that often define a region's geology. Sills and dikes.
Sills and sheets are the horizontal ones. They're layers of solidified magma that force their way parallel to the existing rock layers.
And what's the difference between a sill and a sheet?
Just thickness. We differentiate them purely by their thickness. Thin horizontal layers are called sheets. Thick, substantial horizontal intrusions are called sills.
And finally, the vertical structures, which are incredibly common.
Those are dikes. Dikes are these amazing wall-like structures formed when magma solidifies vertically within fissures, cutting across the existing layers of rock.
And they can be really striking when they're exposed.
Incredibly striking. They often stand proud as a ridge after the softer surrounding rock has eroded away. And our sources point out that these are very common in western Maharashtra.
And again, why that specific region for dikes?
Well, western Maharashtra, particularly the Deccan Plateau region, is characterized by widespread fracture systems and faulting that are associated with the historical Deccan Traps eruption. Those fractures provided perfect vertical conduits for later, smaller intrusions of magma.
So as the plains erode, the dikes are left behind.
As the vast basalt plains erode, these harder, more resistant vertical dikes are often left standing, leading to those pronounced wall-like features you see cutting across the landscape.
That transition from the super hot knife core, driving the convection currents all the way up through the plastic asthenosphere and out through this thin, fractured crust, it truly dictates everything we see and feel. It's one dynamic, interconnected system.
It's a powerful synthesis of extreme physics operating over deep time. We rely entirely on the ability of materials to transmit waves, to reflect their density, and to yield to pressure to comprehend our own planet.
So let's summarize the major insights from this deep dive. If you take away three things, they have to include the cleverness of the seismic analysis, the immense scale, and the mechanical layers.
Absolutely. The cleverness of using S-waves to definitively prove the existence of the liquid outer core. That remains one of the most critical discoveries in all of geoscience. It proved that our planet is built like a massive, churning heat engine.
That S-wave shadow zone is the ultimate geological fingerprint.
It is.
We also synthesized the enormous scale of the Earth's layers. We covered everything from that thin, dense 5-kilometer oceanic crust to the immensely thick 70-kilometer continental crust under mountains, down to the huge knife core, which is pressurized so intensely that its inner portion is a solid crystalline sphere.
And we learned about the dynamic surface expressions, how the viscosity of magma dictates the landscape. We saw the difference between the low-viscosity, non-steep shield volcanoes built from fluid basalt and the highly explosive viscous lava of the tall composite volcanoes that trap enormous gas pressures.
The structure of the volcano is a direct reading of the plumbing beneath it.
A perfect way to put it.
This knowledge is invaluable because it gives you context for current events. It helps us truly understand why we live on a constantly changing dynamic planet where internal stresses and heat transfer dictate every major surface condition, from the location of continents to where the next great tremor or eruption might strike.
We are literally living on a thin skin stretched over a boiling engine.
A very active engine.
And here's a final provocative thought for you to consider, something that builds directly on the material we've covered. We established that S waves are blocked by the liquid outer core, and that P waves slow down dramatically and refract as they pass through it. But they speed up again when they hit the solid inner core.
Right. And that solid inner core is a metallic ball of iron and nickel, spinning slightly faster than the rest of the planet, essentially floating within that churning liquid outer core.
So given that the flow of that liquid iron is what generates the Earth's magnetic field, our planetary shield against solar wind and cosmic radiation, what unexamined impact might the complex interaction of that solid metallic gyroscope spinning independently within a churning conductive liquid have on the long-term stability and the strength of the very magnetic field that protects all life on Earth?
It gives a whole new meaning to internal dynamics, realizing that the core isn't just a static ball of heat. It's a dynamic, spinning, liquid-solid generator that determines whether we survive the radiation from space. Something to ponder next time you feel a tremor or even just look up at the magnetic North Pole.
Thank you for joining us for this deep dive into the secrets beneath our feet.